So, hi everyone. From today onwards, we would be starting a new series on GPU programming for beginners, where we will be starting off with the basics today, and then we will deep dive into CUDA computing and other stuff. So, before starting off GPU programming for beginners, as you must be knowing by now that generative AI is gonna here to stay, and in generative AI, GPU plays a huge role, and hence GPU programming becomes a must for everyone. What I feel, so let's get started. So we will be starting off with all the basic concepts, starting with what is a GPU and how it is different from a CPU. I think most of you might be knowing it by now, but just for a recap, a GPU is a specialized processor. It is not present with all the computers. Do remember this? Designed to handle graphic rendering and parallel computation. Parallel computation is at the heart of a GPU, like in gaming, video editing, machine learning. So before generative AI came in, you must be knowing that GPUs were prominent for gaming. Gaming laptops used to have GPUs. Now, I think most of the common laptops also are having GPU because of the hype of generative AI. It is optimized for executing many operations simultaneously, thanks to its large number of small simple cores. In contrast to a CPU, which every computer has, it is a general purpose processor for handling basic computer tasks, right? Running programs, managing system resources, performing basic calculations, etc. A CPU has fewer, more powerful cores. So in case of a GPU, you have many cores, but they are small. In case of a CPU, you have few, but they are powerful cores, optimized for tasks like requiring complex and sequential processing. So I think this is the core difference between a GPU and a CPU. You might be understanding now. Talking about what is a core, a GPU core is a small, simple processing unit designed for parallel execution. They are good at parallel execution, handling tasks simultaneously across many cores. While a CPU core, it is a more powerful, complex unit, optimized for sequential tasks. It is not for parallel tasks. You can perform parallel tasks, but it is not optimized for that. Do remember this. Now coming to what is GPU programming. Now we have understood what is GPU. GPU programming refers to writing softwares that leverages the power of a GPU, right? So all the languages that we work on, be it Python, be it Java, are mostly focused towards CPU based programming, right? Now we will be talking about GPU based programming that will start using this particular processing unit. How GPU programming is different from normal programming? I think this is very important, and someone asked me this question, so I'm just covering this here. Parallelism. GPU programming, it is inherently designed to leverage parallelism. That's it. It is the core of GPU programming is parallelism. GPU has thousands of small cores that can handle same instructions on multiple pieces. While in case of normal Python programming or like Java programming, they typically run on CPUs. CPUs have fewer cores and traditional programs run sequentially. Talking about the memory architecture, in GPU programming, you need to manage the memory explicitly. I think this is very important. GPUs have different types of memory within them: global, shared, constant. I will be talking about that later in the video. While in case of normal programming, memory management is done automatically, especially in high level languages like Python or Java. So you are not going to optimize the memory, but in case of GPU programming, you need to do it manually. Execution mode. Talking about GPU programming, it involves writing codes that runs on thousands of threads simultaneously. We already understood this. These threads are grouped into blocks, which are further grouped into grids. The threads in blocks can share data through shared memory, but threads in different blocks can't easily communicate. I'll be talking about everything. So this is how the GPU programming executes. While in case of normal programming, be it Python or Java, typically the program runs on a single thread. Multi-threading you might be doing, but that you would be doing explicitly, right? And that too for a very few threads. So don't assume multi-threading to be parallelism in when comparing with GPU programming for now. Assume that most of the time the program runs on a single thread. Now talking about languages and framework. So for GPU programming, we have multiple architectures and frameworks. CUDA being the most popular one by NVIDIA, if you might be knowing. OpenCL is one. TensorFlow and PyTorch, you must be knowing, they support GPU acceleration for machine learning. While in case of normal programming, you already know the languages like Python or Java. Some of the libraries do provide support for GPU acceleration, but not all. Very important question: why you should learn GPU programming? So I will tell you why I am starting off this with series, and I'm also learning with you. So I will be learning a few topics. I will be sharing with you guys. Generative AI is here to stay, and one thing that any LLM requires for inferencing or for training is GPUs and lots of GPUs. I think if you have heard of any model like DeepSeek R, it requires hundreds of GPUs to run. So learning GPU programming is crucial for working with generative AI because of massive computational demand involved in training and running large AI models. You need to understand how to use your GPUs efficiently because you won't be having it in abundance. You would be having, say, for example, if you're working as a student or as a professional also, 8 GBs, 20 GBs, not more than that. At times, you would be having models that require 100 GBs of GPU. How to use them? So, in that case, GPU programming becomes a must. Speed and efficiency. Training models like LLMs require immense parallel computation. GPU with their thousands of cores can perform the same operation on many data points simultaneously, making them faster than CPU. This reduces training time for weeks to days or even hours. So to understand how to efficiently use your GPU for training LLMs, GPU programming is required. Talking about scalability, as models are becoming bigger and more complex, need of parallelism is increasing day by day. Right. So you need to understand how to make your model scalable. And if you don't know GPU programming, you won't be able to do it. Optimized model inferencing. Once the model is trained, how to inference the model in an optimized way so that it uses all your power that you have. It should not be the case that you have 8 GB of GPU, but the model is just using 4. Right. Talking about cost effectiveness, training generative models on CPU can be very, very expensive and time consuming. So you can't go with CPUs in that case. GPUs, especially when used in cloud environment, provide cost effective solution. So to make your training also to reduce cost, you need to use your GPUs to the highest end, and that is why GPU programming is a must. Now, towards the end of this particular video, I will be talking about some basic key concepts that you should be knowing about GPU programming, and in the later part, we'll start off with CUDA in the next video. So the most common term that you might have heard is kernel. So what is a kernel in GPU programming? A kernel is a function that runs on a GPU. Just it is as easy as that. It is a GPU specific function written in any language, be it CUDA, C, C++, or OpenCL, and it is executed in parallel across many threads. So it is a function that can enable GPU for you. Each thread runs the kernel independently, which allows the GPU to perform parallel programming. A matrix multiplication operation can be written as a kernel. So functions, assume let don't call them functions in normal in GPU program, call them as kernels. I would be writing a kernel for this. Assume it like that. What is a thread? A thread is the smallest unit of execution in GPU programming. Each thread executes a kernel independently, processing a small portion of the data. They are lightweight and executes in parallel, enabling GPUs to perform a large number of operations. Blocks. Threads are grouped as blocks. As I think we already mentioned, a block is a collection of threads. Each block runs independently and can be scheduled on different parts of the GPU. So smallest unit is thread. The second hierarchy comes to block, and the third hierarchy comes to grid. So collection of blocks becomes a grid. Grid organizes the blocks into 2 or 3 dimensional structure, allowing the GPU to manage large data sets in parallel. Threads per block. Number of threads present in each block. And this CUDA, for instance, allows you to define how many threads each block should have. A block can contain up to 1024 threads, and this number is often chosen based on the problem and the architecture of the GPU. So this is something that we'll be talking on in the later videos, but just to understand the basic concepts. Now talking about the different types of memory, shared memory and global memory in a GPU. Shared memory is a special type of memory that is shared by all threads within a block, right? It is much faster than global memory and can be used to store temporary data that threads in a block need to access. So all the threads present in a block can use this shared memory, but threads outside this block that are part of another block can't use it. Now, how these different blocks communicate between themselves, or the grids communicate between themselves using the global memory. And as you might have assumed, global memory would be way slower than shared memory because shared memory is accessible by all the threads to a smaller group of people. Global memory would be updated by many guys, shared by many guys. In that case, it would be a little slower. As mentioned here, in GPU programming, it is important to minimize global memory access whenever possible. CUDA threads hierarchy, I think that we already done. Thread, block, and grid. Synchronization. Synchronization is the process of ensuring that threads execute in a coordinated manner, right? If some thread is working now and other is working later, like say after 5 minutes, the data would be unsynchronized. Everything would be mixed up. So synchronization is very, very important. So synchronization between threads within a block is comparatively easy as compared to synchronization between threads in different blocks. Makes sense also, right? So now moving on to the memory hierarchy, I think we already mentioned this. Global memory shared across all blocks and threads, has high latency, very slow and lower bandwidth. Shared memory shared within a block and provide faster access. Local memory private to each thread. So shared memory is shared by all the threads. Local memory is a memory of that particular thread. Constant and texture memory, a specialized form of memory for constant values and read-only data. Wraps, a wrap is a group of 32 threads in CUDA, and they are executed together in a single structure multiple data fashion on GPU. So it is a group of 32 threads in CUDA. It is the smallest unit of execution that the GPU scheduler works with. So this is important concept. Threads can't be executed independently, wraps can be. Compute capability. Compute capability refers to features and specifications of a GPU architecture. I think you might be hearing number of times that okay, GeForce RTX 4090 has come in, it has this specification, this is the compute power, etc. This refers to compute capability. Concluding, I think this was a nice introduction. I don't want to overburden you with all the information all at once. So this is just a gentle introduction to tell you how to get like what is GPU programming, why are you learning this, some basic concepts, so that you just have a hang around of it. And now from the next time onwards, we'll be doing some coding exercises also, and we'll try to learn GPU programming in some depth. I hope this was useful for you.